Okay. Now I got two lessons. Here we go. Here we go. I don't mean for this to confuse you. If it does, I apologize. Hopefully it'll all come together in a second. But before we start this lesson, I'm going a little off note. If f prime is negative until like a value 3, and then positive after 3, what would f look like? Tell your neighbors. Hopefully we're saying thinking f is going down and going up, right? I hope we're saying that. Hopefully we're thinking, this is not supposed to be a trick question here. Hopefully we're thinking f goes down and goes up, okay? Now most of you are probably thinking that it makes kind of like that shape, right? But is there any other type of function that can go down and come back up, but not be curved so nicely like a parabola? Nah, sharp points, I mean, it could be like even a V, even crazier than a V. And the answer is, yeah, what if we were like curving? What if this was F? Would you say that F is going down until 3 and then going up after 3? Yes. But does it look like a nice U? No. Because the curvature changes. Today, we will be looking at curvatures. And we want to be able to tell, like, again, this is becoming better human graphic calculators. We're going to tell, like, how can we analyze the curvature. Is that how you spell analyze? All right. Took me a while. Looks weird. Okay? Now, we start with understanding what happens if slopes are increasing. If f prime is going up, what would f look like? Tell your neighbors. If f prime's values are increasing, what would an f look like so that its slopes are increasing? I like it, Hedrick. Like something like that, right? Right? Yeah, so it's like curving upwards if it's got these slopes that are getting steeper and steeper and steeper. Now, if f prime is increasing, what does that mean? If you think about last lesson and that practice problem we did at the beginning of today, you had the question on your quiz. If something is increasing, what does that mean? Think about calculus. Go. Ooh, I hear some people know the answer right away. Some people are like, no clue. If f prime is increasing, its slope must be positive. F double prime, all of a sudden we are going to look at f double prime a lot more today because it's got a lot of power. F double prime are the slopes of f prime, and if the slopes of f prime are positive, f prime must be increasing. Okay, and then we are going to have a curve like this. What if f prime was decreasing? What do you think f would look like? Give me an example. Ooh, now we got some debate. Cheney, I see you're throwing this guy out there. But then I saw somebody else throwing this guy out here. Which one's right? Or are they both right?
Is it positive or negative?
I'm just telling you that f prime is decreasing. Which one? This is great. And this is gonna like show up next class too as a common confusion among students. F prime decreasing. Well, let's look at like the slopes and just tie in some values to these slopes. Okay, so let's look just at like 3 slopes and just pretend we know the value. Cheney, give me a value for that slope. Just give me a number that like makes sense. Would you say positive 6? I like 6, but I don't like positive 6.
For the slope?
For the slope.
Oh, okay.
Negative 6. Good. All right. Now, Cheney, what about this guy right there? Good. What about that guy right there? Good. Would you say these values are decreasing? Some people would. Some people would be like, yes, Mr. Messner, those values are getting closer to 0. That's like getting smaller, but no. These values are increasing. -6 to -3 to -1. Actually, f primes are going up for this graph. So that's actually part of this graph. Can be like another example of when f prime is increasing. Its slopes are increasing in its values from greater negatives to less negatives. Very interesting. If we had tied values to these slopes, we'd realize this would be like -1, this would be like -2, this would be like -3. This is the correct guy. Here, my slopes are actually increasing, but here my slopes are decreasing. And what you find is that you could have another kind of piece here. Here's another example of when f prime is decreasing. +5, +3, +1, right? So when f prime is decreasing, we know, though, that its slopes must be negative. And what we find is that whether f prime is increasing or decreasing, we realize we have to have this specific type of curvature. And instead of calling things curvature, we're going to call it like concavity. Concavity. And this would be something that's curving upward or concave up. And you can see the slopes would be increasing from greater negatives to 0 to positives to more positives. Now this is like, can be split into half, so it's talking about like 2 different sections. A curving upward decreasing part, a curving upward increasing part. But the slopes are increasing, which means its derivative must be positive. We are going to be creating this chart. This is our step 3, because if we know signs of second derivatives, if we know if our first derivatives are increasing or decreasing, we know if our original function is curving upward or concave up. CC up is what I'm going to use for concave up. It curves upward. Here, my slopes are decreasing from bigger positives to 0 to negatives to greater negatives. We could split this in half into like 2 pieces of graph where we're like increasing curving downward and then decreasing curving downward. We'll call this concave down. We say we are curving downward. And the key to this is that our slopes are decreasing in its value. We will be creating this chart today to understand the curvature. A second derivative sign tells us if the first derivative is increasing or decreasing, which tells us about the curvature of our original function. What we'll find is that curvature changes a lot with functions. And if at a point your second derivative was 0, this would be a point where your first derivative is constant, or your function had like no concavity. No concavity means like you're flat. Function's curvature changes. To be a good human graphing calculator, you got to understand, what is this curvature looking like? You know, we have to add in another type of analysis to step 2, so that if we are told, or if we find in step 2, that f prime is negative until 3 and then positive, we don't assume f is just going to make a parabola. Today, we will analyze the signs of f double prime. And let's pretend f double prime had zeros at 1, 2, 4, and 5. Let's pretend that we found that f double prime signs were positive, negative, positive, negative, positive. I'll let you catch up with zeros in between. We would know that f prime would be increasing, then decreasing, then increasing, then decreasing, then increasing. Sure. But we would know, more importantly, that f would have to be curving upward until 1. Oh, here we go. This is the graph of f. Until 1, f prime is negative, f is decreasing, f is curving upward. Look at that. Curving upward while we go down. Here's an example of a piece of a function that has like concave up, curving upwards for that piece. But then we find for the next section, between 1 and 2, I switch to curving downward. Curving downward. Okay, so f is going down and curving down. We would be able to see and know that my graph has to look something like that, where I'm curving downward. And we could keep doing the same thing. From 2 to 4, I'm curving upward. I go from going down to going up, but I'm curving upward. So here I am curving upward, going down, then curving upward, going up. I'm concave up. And then we keep going. We're concave down, curving downward. We could see right there, curving downward. And we finish up curving upward. Any questions about like what we just created and how this is not sufficient to create a graph that looks like this? What we find is that the curvature changes at these points where these zeros occur of my second derivative. These points are important points. They're called points of inflection. Points of inflection. Points of inflection are where my curvature changes. It's when our second derivative changes sign from positives to negatives or negatives to positives. Similar to like an extrema if we're examining an f prime. Okay? So today, all we're going to focus on is the creation of this step 3. And when we create step 3, we understand the curvature of our original function f. We can answer questions about when we're curving upward, when we have points of inflection. And that's it. We're just going to focus on step 3. Now, next class, what's great is that all we're going to do next class is combine step 2 and step 3. Okay? So we'll be able to like do this and do this so that we could sketch accurately f. Cool? But we don't have to worry about that yet. Today, we're just going to get straight to step 3. We're going to do the analysis of the curvature. It won't help us like determine what the graph looks like. You have to combine 2 and 3 to know the shape of the graph. But we'll just answer questions about like, how is my function curving? Okay? And we're going to skip this part. We're going to get straight to the heart of the matter. This is a little bit repetitive. To test for concavity, here's our step 3. We are going to analyze the signs of the second derivative. We're going to see when it's positive, when it's negative, just to make sure you guys understand. The sign of a derivative tells us if we're increasing or decreasing. If a derivative is increasing, the original thing's curvature is known. Points of inflection are when the curvature changes. And that's when our second derivative changes sign. An example would be like this is a point of inflection. X equals C is a point of inflection. I will use POI for short for point of inflection. Got it? All right. So skip the second derivative test. We'll get to that in a later unit. Oh, you guys don't even have it in your notes. Great. Let's go ahead and figure this out. Please determine when this function is concave down. Let's just worry about concave down. And then also tell me when this function has points of inflection. The function is x to the fourth minus 4x cubed. What would you do? Ready, set, go. Tell your neighbors. Yeah, it's like, that's not that bad. You guys all said, do a sign analysis of the second derivative. Find your second derivative, set it equal to 0, throw down your number line for your second derivative. We're pretty much bypassing step 1. We're skipping over f prime and its sign. Next class, we will be doing both at once. But today, we're just going to bypass step 1, go straight to step 2. We get 2 zeros. We do not call these critical points. They are like the possible sign change locations of a second derivative. They're at 0 and 2. We do a sign analysis of our second derivative. A sign analysis of our second derivative tells us about our first derivative increasing or decreasing. But by thinking about it, if derivatives are increasing, we know that our function has to have a certain type of curvature, or what's going to be now what we say concavity. All right, finish off, like answer the question. When do we concave down? When do we have points of inflection? Like pretty simple if you fill out the chart. We'll concave down from 0 to 2, and x equals 0 and 2 are both points of inflection. Now, you don't know what the original function looks like just by analyzing the second derivative. You know about how it's going to curve, but you have to combine this step 3 with step 2 to know exactly how your function is going to look like. So we don't care about like sketching right now. We will next class. We will combine step 2 and step 3. Now, skip that one, go to this one. Please tell me the points of inflection for this function. All right, go, 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 go. Tell your neighbors, what do you get? So I kind of want you guys to like have a little bit of uncertainty with this example. Okay, I want you to be a little bit like, well, what the heck does that mean? If our second derivative sign's analyzed, and we do a correct sign analysis of our second derivative, we realize that we only change signs at -3. F prime decreases, flattens out, then increases, flatten out, increases, which means F is concave down, then concave up, but then concave up after that. Like, what the heck does that mean? Well, it turns out x equals -3 is our only point of inflection. Okay? This is the only location where our second derivative changes sign. So then you're probably thinking, okay, cool, but then what the heck's going on there? And the best example I can give you is to look at the graph of x to the 4th. I'll just walk you through this one. So x to the 4th, its second derivative is 12x squared. And the second derivative has a 0 at 0. This is the previous question in your notes. So the second derivative is positive, then 0, then positive, which means the first derivative is increasing and increasing. And I'm actually going to compare this at the same time to y equals x squared. Now, y equals x squared, second derivative is 2. Now, what does this mean is that y equals x squared, its second derivative is positive everywhere, which means y equals x squared is curving upward everywhere. This is something that makes sense to you. A parabola curves upward, right? So y equals x squared curves upward. But then you think about the graph of y equals x to the fourth, and you're like, isn't it like the same as x squared? And doesn't it just curve upward the entire time? Well, actually, it doesn't. Okay, see this red graph? The red graph is y equals x squared. Y equals x squared, yeah, it curves upward the entire time. Its second derivative is positive 2, so it's got that type of curvature. It appears that x to the fourth does the same thing, but actually it's a little bit different. What is going on, I don't think I can show you, but I can highlight it. What is going on is that it's very similar to behavior, but as we get closer and closer to 0, it flattens out significantly more than y equals x squared. So much to the point that it has a point right here at 0, which is a point of no concavity. Now, this is kind of like one of those neither situations. It's like points with no concavity don't necessarily mean we're going to have points of inflection. Here we have flattened out enough that there is a spot on y equals x to the fourth that has no concavity. That's essentially like a straight line. But then everywhere to the right and to the left is curving upward. Okay? So that's what's going on here with this example. X equals 0. It's a point of no concavity. It's a point, if you looked at the graph of this, where you'd see the graph is flattened out significantly, so much that there is a point with no concavity, but then to the right and to the left of it will be concave up. We're not going to label it though. Like, it's not going to affect our answer. I asked you to find the points of inflection. You say x equals 3 is the only point of inflection. Cool? All right, great. What you found is that, like, this stuff is very similar to what we've already been doing. So I'm not going to spend that much time like doing another example, because it's like no big deal. I can go ahead and like take the derivative twice and then do a sign analysis. So you're right. It's very much the same thing, just with an extra derivative. But where we'll see difficulties are on the graph questions. Now, we've already got the hang of the graph questions with our first derivative for maxes and min. Okay, so here again is the graph of the first derivative f prime. But the questions are not about maxes and mins. The questions are about points of inflection on f. Where does f have a point of inflection? And then I want you to tell me, when is f concave down? I'd like you to try this right now, because I need you to make mistakes. Right now is the time to make mistakes. If you don't try and if you don't make mistakes now, you won't realize like how tricky this can be until it's too late. So ready, set, go. Try to tell your neighbors, what is the original function f curving downward? Go. What is the original function f going to have points of inflection? Go. Try it out. I want you to try and get it wrong. I need you to do it. This is important. You got to see how this is funky. Good job. If you got it right away, great. If you don't, you're right where you should be, which is like, oh, this is different. So a lot of us know what we know. A lot of us know what we know, and what we know from last class is F prime's analysis. Yeah, but F prime's analysis tells me about F going up, going down, etc. I don't want that. So if you were focused on -3, 1, and 3, yeah, of course, that's what you know. It's like, I know to find the zeros of F prime. But now we got a whole new situation because it's not about F prime signs, it's about F double prime. Now, what's great about this is that there's multiple ways to kind of handle things. I got F double prime that's going to tell me about F prime, that's going to tell me about F, right? Well, the way that the chart works, and I'm just going to, throw this down here just as a quick little chart example. This is not for this question, but just like an example. If F double prime is positive, F prime is increasing, F is concave up, right? It goes the same way the other way. Okay. What do we have? We have the graph of F prime. Okay, well, we could tell about when F prime is going up or when F prime is going down. That's one way to be able to figure that out. What's another thing? Oh, F double prime signs. Well, I know that F double prime are the slopes of F prime. There are two ways to be able to fill out the chart for F double prime when given the graph of F prime. You could either focus on, let's do this in red, the slopes of F prime. And you could say, oh, the slopes are positive, positive, positive slopes, zero slope. Oh, -1 is important, positive slopes. And then negative slope, negative slope, negative slope, another zero slope at 2. And then positive slopes, positive slopes, positive slopes after 2. Cool. You can fill in the rest of the chart after that. Or you could look at, my bad, you could look at F prime's direction. F prime is going up, then it's going down, then it's going up. You could go straight to F prime increasing or decreasing. You could have gone straight to this level of our chart, and you could confirm the other level from there. And that's how you know about the curvature of F. So if you did not recognize that right away, that's fine. You didn't know to do that, now you will. One of my concave down from -1 to 2, F is concave down. When do I have points of inflection? -1 and 2. All right, so we realize it's going to be different. It's different than last class. Let's see if we can handle this one. Change that to concave up. We've been stuck on concave down for too long. All right, tell your neighbors. Maybe we got this one. Maybe this is like piece of cake now. Maybe we're getting 2 in a row.
Yeah. Or negative.
You got it. Everything's good. Now, forgot to tell you that these intersections are at -1 and 1. Does that change anything? Doesn't change anything. There's just like a little fake out there. F double prime, the slopes of F prime are positive then negative, or F prime is increasing then decreasing. When is F concave up? When x is less than 0, or from negative infinity to 0, because that's when F prime slopes are positive, or when F prime is increasing. Where do we have points of inflection? At x equals 0. Cool? Nothing crazy, right? To the left of -1, I don't care that F prime is negative. All I want is for F double prime to be positive. All right, so we feel like we got a handle on things. Everything's good. We have our phones out. We don't really care. The rest of the lesson's boring anyways. This is just repetitive. And then we feel so good about ourselves. We're skipping questions on the homework, whatever. I'm just going to watch the video. I'll fill it out later. This is a piece of cake. And we end up skipping over this question. We have this under control. Yo, buddy, you copy down the homework. Let me just copy down off of you. And then you get to the quiz. You answer this just like you did the last two questions that we did, and you get it wrong, and you have no idea why. Please answer this question. Again, same deal. We'll go back to concave down. When is F concave down? When does F have points of inflection? Obviously, it's got to be -1 and 1. You know, we've just been kind of doing the same things all the time. Wait, no, -1 and 1. Those are fake outs. No, it's got to be 0. It's got to be x is less than 0 again. This is a piece of cake. I got this problem. No problem. I need you to try right now. This is the one that's going to trip you up. If you are I've done it once, I've memorized the process, I'm good. These are the questions that will destroy you on the test. What we realize is that since this is the graph of F double prime, and since we want to fill out an F double prime sign analysis, actually -1 and 1 matter. They're not fake outs. They're when F double prime equals 0. This is like what we had on our quiz today. Only it's just an extra layer down. We don't even know about F prime increasing or decreasing. We can't say F prime is decreasing. F double prime is decreasing. Ooh, that means F triple prime is negative. Let's not go there, okay? Let's not go there. We will just look at the signs of F double prime, but sometimes you might be given the graph of F double prime. And that's telling us about F prime. And then that's telling us about F. So we feel like we got things under control, but then lesson 2, lesson 3 messes us up. So -1 and 1 are points of inflection, and from -1 to 1, that interval. All right, so we feel good about ourselves. Everything's great. And then we get this question. Again, we just skip the rest of the homework. Who cares anyways? It's a piece of cake. Everything's just repetitive in this class. I just do one. I do them all. Mr. Messer throws in some crazy stuff about like locations of maxes and mins for this problem. He even tells us there's a point of inflection. Fantastic. It asks you, when is f double prime less than 0? All right, answer this question. Last question. When's f double prime less than 0? Wait, don't leave. You could graph f prime, graph f double prime. Don't do it. Wait. But this is the same as when is f double prime negative, which is telling me when f prime is decreasing, which tells me when f is concave down. Wait, what am I given? The graph of f. I'm actually asked, when is that graph concave down? The answer is x is less than 1. If you got that, great. If you didn't, guess what? This stuff is not easy just because it looks the same. Okay? So, depending, you will be given graphs of f, graphs of f prime, graphs of f double prime. Yes, you might need a map. This stuff is, yep, I'm just smacking you guys around. At least you're honest and you recognize that this is tricky. And now all of a sudden it's like, wait, what? Yes, good. You're right where you need to be. Make sure you struggle and do the graph problems, guys, on the last 2 pages. Do the graph problems like you've never done them before. I don't see you until Friday.
All the Ben kids won't be here on Friday.
I won't be here.
Well, then you guys will have to catch up on what you missed.